Hi, my name's Dan, and this video is one in a series that I'm doing on logic circuits in digital electronics. This series is kind of an introduction uh, to some of the ideas in logic circuits, and in this one, I'm going to be showing you how to use truth tables to create logic circuits. Okay, so in order to understand this, you need to understand the basic gates and something about Boolean logic, and to understand what a truth table is. I think that's fairly obvious. And what we're going to do is we're going to revisit, first of all, an example that I had in the last video, which is about British traffic lights. So we're going to look at the cycle of the lights. Now, last time, uh, if you watched it, you would have seen that the British system of traffic lights gives you four phases. The first phase is where you've just got a red light, and then in preparation for green, you've got a yellow light under the red, and then the third phase is just a green light, which means when you can go, and then the fourth phase is telling you that it's about to go back to red, which is a yellow light on its own. And last time um, we did this using four distinct lines, one for each of the phases. We've got four phases, we've got three lights, and that was a fairly straightforward example. However, there are some problems with doing it like that. One is that if something goes wrong, it would be possible to be trying to have more than one phase at once because you've got four distinct lines. So another way of approaching this is instead of having four distinct inputs, we're going to use a binary input for this. So there are four phases. Um, in order to get four numbers in binary, we need a 2-bit binary number. And it's safer, but it does make the problem more complicated. Well, that's good for us in terms of learning. So also, it's a nice example for showing the use of truth tables. So let's explore what this actually means. We've got the four phases. We're going to use the 2-bit binary numbers to represent the four phases. And I've just put those underneath the phases on the light. 0, 0, 0, 1, 1, 0, 0. Yes, I've written that wrong, haven't I? That should be 1, 1 at the end. Let's just ignore that and think that that's 1, 1. I'm sorry I've made an error, but that won't translate itself into the actual circuit, so let's not worry. And in fact, the truth table that we've got is correct. So A and B, we're going to use those for the 2 bits of the binary number. A for the most significant bit, B for the least significant bit. So we've translated the states from the picture into the truth table. So on our 0, 0 phase, we've got red showing, but not yellow and not green. On our 0, 1 phase, we've got red showing and yellow showing, but not green. On our 1, 0 phase, we've got red's not showing, yellow's not showing, but green is showing. Then our final phase, 1, 1, where I've got it wrong under the picture, but it's right in the truth table, is 1, 1. And then red's not showing, yellow is showing, and green's not showing. Okay, so what I'm going to do now is I'm going to go across to Digital Works, which is the software that I've been using to show digital electronics. It's a simulator. A link to where you can get it will be in the description down below if you want it. And I've got a series of videos on how to use it before this one. And I'm just going to zoom in a bit. And I've transferred that truth table that I had in the nice slides across into Digital Works. I've just done this using annotations, just so that we can remind ourselves what we're doing. So we've got 2 inputs, A and B. We're going to have a binary number coming in this, and we're going to have 3 outputs. In fact, we're going to link them up to LEDs, a red LED, a yellow LED, and a green LED. So let's get those 3 LEDs in first. 1, 2, 3. And as often happens, I end up with an extra one because I'm using control as I click to give me extra ones, give me more of the same thing. I'm just going to line them up slightly, not that's going to be that important. And that one's already red. I'm just going to change the colour of this one to yellow. Yellow, and then the bottom one's green. Okay. And I'm going to give us 2 inputs. Actually, I'm going to start with 1 input because what I'm going to do, and this is a fairly typical thing to do when you're using truth tables to create digital circuits, is that we want to create two lines. One which represents, so if this is the A input, one represents A and one represents not A, and we can tap off either of those. You'll see what that means in a minute or so as we get going. So the first thing I'm going to do is I'm going to create a wire that comes down, and in order to do that, I can either use a tag device, or in fact I'm going to use an extra LED just down the bottom there to connect that wire to. Straightforward. And I'm going to create a parallel line to this, which I can use if I want not A. So I'm going to put the not gate in, twist it around, and just stick that in there. I'm going to put another LED down the bottom just for connecting to. So these LEDs kind of give you a visual thing. They're not important in terms of the circuit. I could have used a tag device. As I said, I'm going to connect that up. I'll connect that up there. So this line here represents the state A, and this line here represents the state not A. So if we want to use A, then we want to tap off by creating a wire from here to wherever we're going. I'm just going to delete that one. And if we want not A, we're going to use the other one here. Yes. Okay. So that's A, and the reason why I haven't done B yet is because I'm just going to copy and paste that to give us a second line for B. And I'm just going to put annotations in there so that I know what I'm doing. Across a bit. So that's my A line. And B line. Okay. So if using truth tables, if you can make a truth table for, oh come on, stupid thing. I've accidentally rotated my B. Yeah, and other phrases you never thought you'd hear. Right. As I was saying, if you've got a truth table, then you can always make a circuit. It might be more complicated than you need, but it is always possible to make a circuit from a truth table. And in fact, we've effectively got three truth tables because we've got one for red, we've got one for yellow, and one for green. We've combined them all together into one truth table. So let's look at the red first. So the red light is on when, for which digital, which binary numbers? For 0, 0 and for 0, 1. Okay. So thinking about this in terms of Boolean logic and in kind of talking it through in human words logic, the red light is shown when A is off and B is off, or when A is off and B is on. Okay. And we can take from these inputs, we can represent any of these binary numbers by using an AND gate. So if we put an AND gate here, and in fact I'm going to need a few of them, but two to start off with. So if we want 0, 0, we need to connect that to the wire which is when A is 0, this line is high. One thing that I found an easy way to remember this, it can get a bit confusing trying to remember, do I want that wire or do I want that wire? And I use this little bobble on the NOT gate there as an indicator, and I think when I want a 0 for this line, I want the one with the 0 on it. And so I want A is 0. Come on, where's it connecting? That's just slightly too close to attach. So I'm gonna. So when I say too close to attach, it's slightly too close to the NOT gates, and it's inside the picture of the NOT gate, and it's not attaching. So attached to 0. So this top AND gates, this will be true on the output when our input is 0, 0. And then the second one we want is 0, 1. So I'm going to connect that to the 0 line for A, but for the 1 line for B, which is the one that doesn't have a NOT gate on it. Okay. And if either of those conditions is true, then we want our red light to be on. And the word either indicates that we want an OR gate. So we can connect that up. And this is how you go from a truth table to a circuit, is that you're almost always going in terms of you have a set of lines representing your binary input or your inputs, and then you use, for however many conditions you want to be true, you use AND gates. And if you've got more than 2 inputs, you might need multiple, like 3 or 4 input AND gates here. And then you take all of the ones that you might want into an OR gate to connect them together, or multiple ORs if you need them. And that's going to be our red wire there. Okay, so I hope you kind of follow that logic. We're going to do the same thing now for the yellow. So once again, we've got 2 conditions where the yellow light is on. We've got input 0, 1 or input 1, 1. So we're going to need 2 AND gates again. That's going to be the 0, 1, 1, and that's going to be the 1, 1, 1. Doesn't matter about exactly how close. So 0, 1 is going to connect to the 0 line there and to the 1 line there. And what did I say? 1, 1. So I'm going to connect to the 1 line there and the 1 line for B. And once again, we need an OR gate at the input. And that up, and that's output from that is going to go to my yellow light. And then finally we're going to do the green light, and the green light is only on during one of the phases, and that's the phase where the binary input is 1, 0. So once again we need an AND gate, but we only need the 1 because we've only got one condition that satisfies the requirements. And because we've only got one, we don't need an OR gate at the output. We just need to connect this in, and it's 1, 1, so we need to go to the 1 line of the A and the 1 line of the B. So it wouldn't have mattered if I'd used the tops and the bottom inputs of these AND gates interchangeably. It tends to be good practice to do them in a particular order. And generally speaking, you tend to have binary numbers if they're written horizontally, or if you think about them horizontally as inputs, in the same order that you would think of them as a binary number. So with the most significant bit to the left-hand side and the least significant bit to the right-hand side. And then when you're doing them vertically, you tend to, again, go from top to bottom, most significant to least significant. And that's because if you're writing text that goes that is vertical, again, you read it from top to bottom, and so it makes more sense to do it from top to bottom. Anyway, let's connect to Python in light. Now, hopefully, we can do a proof of concept, and we're going to switch it on and check our 4 potential binary inputs, and our LEDs down here aren't really signifying anything. That we're just there to connect to is the things that we want to look at are the red, yellow, and green here. So 0, 0 input, we've got a red, no yellow, no green. Just put the B on, and we've got, so 0, 1 input, we've got red and yellow, but no green. And then switch that off in order to put that on. So A input, Something's gone wrong here because I was expecting this to be on. Now, why isn't it? Um, 1 0. That's because I've done my green wrong. I consistently said it was 1 1, and it isn't. It's 1 0 that I want. And maybe sharp eyed ones amongst you have spotted that. So I'll delete that wire and put it back into the correct thing. This, obviously, as a lecturer, I'm going to say that this demonstrates the need to test things. Let's run this again and check. So we'll start again. 0 0, the red light's on. 0 1, red and yellow. 1 0, the green light's on. And 1 1, we've just got yellow. So that is the solution to our problem. We've gone straight from the truth table to logic gates to giving us the desired output. Now, you may have noticed when looking at this that there are actually things that we could do to reduce the number of gates that we've got here, but I'm not going to explore them in this video. The next couple of videos in this series, I'm going to look at two different ways to do reduction of the number of gates that you're using in circuits. One of them using Boolean algebra, and the second using a thing called Carnot maps. However, what we're going to do now is we're going to do a different example, again using truth tables. And I'm just going to delete a whole lot of stuff from there, but I'm going to hopefully let's just delete the whole lot. I'm going to reconstitute those. So let's go back to the PowerPoint. I'll zoom out and go on to the next slides. Right, so example 3. I know it's only the second example in this video, but we had example 1 in the previous video and example 2. We've done example 2 twice. Example 3, we've got numbers being input, and in decimal, we're going to want our output. We're going to have a single output. We want our output to be true when our input is decimal 10 or decimal 11, and not under any other circumstances. Okay. And so we need to convert that into binary. So that's binary 1010 or binary 1011. So this is a bit more of an abstract example. And I guess the question would be, why on earth would you want this particular example? And the answer might be because some evil lecturer has set you it as some kind of assessment. So we're going to come back to Digital Works now. And I've set some stuff up in anticipation. So the first thing that I've done is that I've written out the truth table. It's a little bit of a pain doing this in Digital Works, but it's actually fairly useful to have this visual reminder of where we're going. And although I've highlighted the two conditions where we want a 1 on the output, I haven't actually put that in. So I'm just going to edit those annotations so that we know that. So I've bolded the two conditions where we want a true output. And I'm going to put an LED in and call it Z. So this is going to be my output. It's fairly traditional to have outputs called Z or something like that, and to have inputs called A, B, C, D. And who am I to break tradition? So we want this light to light up for the binary numbers 1010, which is 10, or 1011, which is 11. Right, the first thing I'm going to do is I'm going to show you it's done incorrectly. Okay, so when I jokingly said that this might be the sort of thing that you get in an assignment, I have had an assignment that I set which was very similar to this. And I saw a lot of solutions which were quite like this. So we need AND gates. Feeding into an OR gate, we've got two conditions, and in this particular version, I'm going to have a 2-input AND gate and a 3-input AND gate. I'm going to feed those two into an OR to give us our output. Bear in mind that this is incorrect, so please make sure you don't do it like this. And I'll show you the correct way in a second. So I'm going to plug everything up together. And then, so the two conditions, 1, 0, 1, 0. So A is true and C is true. So I'm going to use A to be true and C to be true. And then 1, 0, 1, 1, which is A is true, C is true, and D is true. A is true, C is true, and D is true. Okay, let's simulate. And the students who produced solutions like this no doubt tested them and tested them like this. So they got A is true and C is true, gives us a true output. So 1, 0, 1, 0 does in fact give us the correct output. 1, 0, 1, 1 does in fact give us the correct output. However, 1, 1, 1, 1 also gives the correct output in this case. Also gives us a true output, which is incorrect. And what they have failed to take into account, students who did this in the assignment, was that you don't just need to hit the correct output when the input is correct. You also need to make sure that the correct output, which is a 0 for all of the numbers, is also correct. Okay, so let's stop the simulation and get rid of some of this and show you how it should be done, which is that you need to use all 4 inputs and use the true and the not true, so the 0 and the 1 conditions. So once again, we do only have these 2 situations in which we're going to have a 1 output, so we just need a single 2 input OR gate. But we need to use 4 input NAND gates and 2 of them. Okay, so I'm going to do 1 there. I'm going to change this inputs to 4 and then copy and paste to give us a second one. I'm going to wire those up to the output. So what we've got, 1, 0, 1, 0. So if you remember from earlier in this video, if A is 1, we're going to want to connect to the file line there. B is 0, we're going to connect to the B0 line. Remember, I used this blob on the NOT gate as an indicator that this needs to be a 0. And then this is our C line 1, 0. And similarly, 1, 0, 1, 1, 1, 0. And these both connect to the 1 lines. There. Right, so I'm going to simulate, I'm going to try going through all of the binary numbers to test this. So 0, 0, 0, 0, off, 0, 0, 0, 1, off, 0, 1, sorry, 0, 0, 1, I'm not going to read them all out, let's just go through them all. Off, off. Excuse me. Off, 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 off. On, that's correct. On, that's correct. Off, 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 off. And so I've shown that, hopefully, demonstrated that we've got the correct outputs from the correct inputs in this circuit, and we've done it using a truth table. Again, there may be ways to reduce the number of gates that we've got here, and we're going to explore those over the next 2 videos. But that's it from me for now.